So large scale structure of universe and like inflation in the universe. And whenever we like hear about the Big Bang, people call it like it wasn't a bang, it was an inflation. So where does these theories came from? Like it was not a bang, it was a inflation, and the universe is constantly inflating at an accelerating rate. So
Yeah.
how does this work, and how people say that that was an inflation, not a bang?
No, so the point is, uh, again, opinions vary, but if you have an idealized model, which is what we started with, that the universe is smooth everywhere, and then use general relativity, the ideal model tells you that there will be a time in the past when the volume of the universe will go to zero. And that's called Big Bang, right? And it's a singular point. So it's whenever we encounter infinity in physics, the general tendency is to assume that there's something more we will discover. And what we expect that will bridge that part is quantum gravity. Because our understanding of the universe, the in lab or the fundamental interactions in the universe, the particle, the highest scales that we look at the Large Hadron Collider, maybe their cosmic ray that are coming at much higher energy, but nothing comparable to the energies that we need for the earliest moment of the universe. So if you just, you know, ideally push the clock back, you will encounter a time when the universe was so hot that you have quantum gravitational effects that you have to take into account. So that general relativity will break down at those scales. So to me, I mean, this is a point of view. I feel that as human beings, we are exploring the universe and we are kind of unwrapping what we know about the universe that we can base on confidently on physics that we know of and observation. That way, we have pushed the boundary fairly far, right? On basic physics, I told you, nucleosynthesis is there are two independent ways we have verified that nucleosynthesis kind of thing must have happened. So that takes you to energies of 10 billion kind of Kelvin, right? The universe is as hot as that. Now beyond that, yes, there are theories of high energy physics which we have verified to large extent. If they are true, then we can extrapolate what must have happened in the universe before that. So there must have been quarks, plasma from which, the fundamental particles like protons are now formed. That takes you further. Then you ask, there's a fond hope in particle physics that if you go to a high enough energy, all the three interactions, apart from gravitation, they become a common force. And that is encouraged because we used to look at electric and magnetic fields magnetism and electricity as separate phenomena. And Maxwell told us they are one and the same thing, right? Moving charges, create magnetism, and static charges are what we learn as electrostatics. And then going forward in the 1970s, we unified the electromagnetism with what we knew as weak force, weak nuclear force, right? Which was a spectacular thing. It was verified, and the Nobel Prize is given for that. Now, if you extrapolate that, then you need the strong force, which is what we call the nuclear forces. We hope that will also these all three things that we see separately, electromagnetism, force, and strong force, can become one common force. And that energy is, uh, 10 to the power of 16 billion electron volts. Just to compare, the LHC is operating at 5 to 7 TeV, right? Tera electron volts. This is giga electron volts, and then remember you're putting 16 zeros additionally. So these are enormous energies. So we can't hope to probe them in lab, right? There won't be a, let's see, the best arena we have to test this idea is cosmology, because in cosmology, if we take the expanding universe, go far back, we would have encountered such energies. And the question is, what are the predictions? And one of the predictions are these fluctuations that we see in the microwave. So it's very vital to establish that the fluctuation in the microwave background originated from physics at a given energy scale. What is called the GUT scale, GUT, Grand and Unified Theory scale, is 10 to a 16 GeV. And so that is what I feel is a very exciting frontier, because it connects the cosmos to the, tiniest scale in physics, which is what we know.